Because we all know, last time we did the Laplace marathon, and it was really fun. But have you guys ever wondered, shouldn't we be doing the inverse Laplace marathon as well? And of course, the answer to that is yes. So in this video, here is the inverse Laplace marathon, and we have a total of 24 of them. Honoring Kobe Bryant, so total of 24. And this file is in the description for you guys already. Go ahead and download that and work it out along the way. Right? So let's just go ahead and get started right here. This is the notation for the inverse Laplace, and you see that the inside is an expression in terms of the s, right? So we have the function in the s world. We have to go back to the t world. Now, before we start, I actually have to tell you guys, here's a challenge when you're doing the Laplace or the inverse Laplace, especially for the inverse Laplace. You have to know how to write the s and also the 5 really well, but I can't. So here is the deal, right? In this video, when you see this right here means 5. And if you see this right here is the s, as in super or supreme, or whichever word that you like with s, right? So that's my challenge as well. In this video, all the s's will be in red, right? So if you see something like this, I'm trying to say that's a 5. Anyway, enough talking. Going back to the s world, you just have to remember the things that we did really well, and we just have to go backwards. This is the one that you have to know from what we did last time. Note, if you have the original Laplace of t to the nth power, this right here is equal to n factorial over s to the n plus 1 power, like this, right? Again, just have to remember the formulas and all that stuff. And you see this right here matches that. When we have to go backward, we can expect to have t to the nth power also. Now, look at this and look at that. We can see the n has to be 3. But the problem is that we do not have 3 factorial on the top. But it's okay. This is all we can do. So here we go. Let me just write this down again. Here we have the inverse Laplace. On the bottom, we have s. And then, again, 4 is the same as 3 plus 1. That's good. N is equal to 3, no big deal, but originally we only have a 1. That's no good, but it's okay because we could just do the following. Here is the 1 that we have, but we can actually just multiply by 3 factorial to make this into that form, right? However, if you just multiply by 3 factorial, of course this is no longer the same as the original, but it's okay because Laplace is linear. All we have to do is on the outside, just go ahead and divide it by the constant multiple. I just multiplied it, namely, go ahead and divide it by 3 factorial. So that's pretty much it. And as you can see, here, work that out, 1 over 3 factorial. 3 factorial is 6, because 3 times 2 times 1, so you have 1 over 6. And then, for all this, n is, again, 3, so going back, we will get t, and the n is equal to 3, so we have 3, the third power right here. And that's it, right? So this is the one that you have to remember, and later on we'll just kind of do this in our head. Now, question for you guys. Do we need to put on a plus c? No. Good. All right. This is the inverse Laplace. All right. Anyway, first one. Pretty cool, huh? Now, second one. Here we have the inverse Laplace, and we have 1 over 6s plus 3. 6s plus 3, all right? In my opinion, it's really evil if you assign a question like 1 over 5s plus 55 or something like that. See? Anyway, I'll stop complaining. Okay, so for this one, we have to use a different one. Well, here is the deal. I will just recall all the things that we did from the previous video for you guys. The original Laplace of e to the at power. So again, I'll just make the a in blue, at power. This right here will give you 1 over s minus whatever this a is. So we have 1 over s minus a. But here is the trouble. Right here, we have a 6 times s. So to fix that, likewise, this is a plus, this is a minus. So we also have to fix this. But it's okay, we can just do algebra for this. So here we go. Well, we have the 6 right here. And again, just like what we did earlier, we can multiply things and divide things and all that. And in this case, we can factor out the 6. And then we can take that outside of the inverse Laplace. Because Laplace and inverse Laplace, they are both linear, all the stuff. So let me just write this down right here. This is the original question, the inverse Laplace. 1 is still on the top over this 6. I had to factor out to the front. So let me just put down as 1 over 6. And then 6 as earlier, now it will just be s right here. But here, it was a 3, but we factor out the 6, so it becomes 1/2. So remember that. All right, so technically you should put parentheses like this if you want to make it super clear. And then the plus, well, look at the plus as minus minus, like this. So we have a minus 1 over 2, like so. And that's pretty much it. This right here is the form that you need to go back to the t world. Well, here we have the 1 over 6. And to go back, of course, it's just e to this power times t. Therefore, we have negative 1/2 right here. And then we multiply by t, like this. Done. Do we need a plus c? Of course, no. This is the inverse Laplace, right? So that's pretty much it, right? So just continue with number 3. I think I should be able to write down another one. Yeah, let's do another one right here. Number 3, we have the following. We have the inverse Laplace of s plus 1. Again, s in red plus 1 over s in red and then plus 2, like this, right? Now, here is the deal. On the bottom, you can see that we have s squared plus 2. This is the time that we have to use the sine or cosine. And in fact, we have to use both. You will see why. Here, let me just write down a note again for you guys. Right? Remember that the original Laplace of sine of bt, right? This right here gives you b over s squared plus b squared, like this. And then we also have the Laplace of cosine bt. This right here gives you s over s squared plus b squared, like that. So these are the two that we have used. Well, on the top we have s plus 1. On the bottom we have this, right? So we'll have to actually break down the fractions. So here we go. For the first one, we will write it down as the inverse Laplace. And then let me just write s over that. So we have inverse Laplace. And the inside is s over, this is s squared plus 2. Well, because of the formula like this, we have to really look at this as b squared. So don't look at the 2 as 2. Look at the 2 as square root of 2 squared. So this right here, I will add square root of 2 squared. So that's actually the first part right here, right? Now, we add, again, inverse Laplace is linear. So that means you can break this apart. So the second part is the inverse Laplace. And the denominator will stay the same. So we have this, again, s squared plus, we'll write it as square root of 2 squared as well. Yeah. And right here on the top, we have 1. So that's what we have, right? This is just the same as this. However, in order to go back to the t world, the first one is ready. But the second one, this right here, is not ready. Why? Because the top right here, we should also have the b when we go back to the sine of bt. But it's okay, because we can do the things just like this right here. We can multiply and just remember that we have to divide. That's all. So here is the deal. This right here is ready. The b is just square root of 2, so that's very nice. However, for this one, this is square root of 2. On the top, I really want to see the b right here as well. So I will have to multiply by square root of 2. And then just remember to divide it by square root of 2 in front as well. So that's all we have. Now we can go back nicely. The first one is the cosine one, with the s on the top is the cosine one. So we have cosine. And by the way, when you have the cosine, the s doesn't have to be in red, right? Life doesn't have to be that hard. Cosine, and then the b is square root of 2. And then, of course, you have to have the t. And then here we have the plus 1 over square root of 2. And then this is the sign version. So just write down sine of square root of 2 t. And hopefully one day I know how to hold 3 markers in one hand, and that would be so cool. But anyway, I don't know. Here is the answer for the third one, like this. All right? So pretty cool, huh? And again, this should be a closed parenthesis. You guys can see that. All right. So this is pretty nice. This is the inverse Laplace transform. And I don't know if you prefer this over integrals or not, but unfortunately for the inverse Laplace, we can only do so many in terms of how many types. And by the end of this video, I'll show you guys how to use the inverse Laplace and also the Laplace transform to solve differential equations. So if you haven't done that before, this is the time. All right, so let me just erase this right here. Yeah. So here is number 4. Here we have inverse Laplace of this and that. And again, let me know how you guys are doing. Hopefully everybody is doing well. All right, here we have 1 over, and this is s squared plus 2s. S squared plus 2s. Now, let me just tell you guys, when we are doing the inverse Laplace transforms, you're expected to know your partial fractions really, really well. And of course, we have done that a lot back in the Cal 2 days and also the integral days. And you really need to know how to use the carve-out method. It's going to save you a lot of time. So just like this one, s squared plus 2s, we can factor the s on the bottom first, right? So if you do that, you see here we have s, and then we will just get s plus 2, like this. So this is a product of 2 distinct linear factors. Right here, we can just write this as the inverse Laplace. And let me just put down like this. To do the partial fraction, we will know we will have a number over the first factor, which is just s, plus another number over s plus 2, like this, right? And now here is the partial fraction with the carve-out method. To figure out this number, which has an s on the bottom, we go back to the original and carve up the same denominator. And you ask yourself, how can you make s equal to 0? Well, I just told you the answer, s has to be 0. And then you plug in 0 into this s right here, and then just work that out. 1 over 0 plus 2, just 1/2. So we just get 1 over 2 on the top. This is the 1 over 2 on the top, right? And then to figure out this number, you go back to the original and cover the same exact denominator, and you ask yourself, how can you make s plus 2 equal to 0? S has to be negative 2, and you put it right here, and then we will have 1 over negative 2. So this number is just going to be negative 1 over 2, like this, right? And then, of course, you can just go ahead, do the following. Well, here's the deal. This is s to the first power, right? Which is the same as saying s to the 0 plus 1. So it's going to be t to the 0th power. On the top is technically, you can just look at this as 0 factorial. Well, anyway, whenever you have 1 over s to the first power, when you go back to the t world, it's going to be a constant. So that constant, in this case, is just 1/2 times 1, so just 1/2, right? So again, if you take the original Laplace of this, you'll get back to that, right? Next, let's put down the constant multiple, which is the minus 1/2. And this time, this s plus 2 is the same as saying s minus negative 2, right? And this is the one that has the e, right? E to the at power, and the a is negative 2. So we have e to the negative 2t, like this. And we are done. So again, know your partial fractions really well. This is like the combination of question 1 and question 2, right? Okay, now let's look at the 5th one. We have the inverse Laplace of, okay, this is 5, of, we have s over s plus 2, over s plus 2 square, like that, right? We can do some partial fractions if you like, or you can do the partial fractions this way. In math, the most important thing is that you need to know how to make things happen. Sometimes it just works out so nicely if you can just see the picture and then just kind of work it out. Yeah, I'll show you how. Here is the deal. Let me write this down again, right? So let me just show you. Here we have the inverse Laplace. Let me just write down the original one again. So we have s over s plus 2 squared, yeah? Now, this is what we'll do. On the bottom, this is s plus 2 squared. So that means s plus 2, yeah? And just think about it. Ask yourself this question all the time, right? Wouldn't it be nice if on the top we have s plus 2 as well? Yes. Why? Because s plus 2 and one of the s plus 2 can cancel out, right? That's really good. Well, in that case, can I produce the s plus 2 like so? Sure, I can, right? Why not? I can just add 2 to it. But that changed the whole thing. That's no good. But don't worry. As long as you remember to minus 2, it's okay, right? Because they are equivalent. Now, check this out. Again, we'll break this apart. Look at this over that. This and that will cancel. So we actually just have the following. Inverse Laplace. And let me break this down for you guys. We have 1 over just this to the first power, right? Just this to the first power, because again, this and that cancels, which is very nice. Then, for this part right here, we have the minus 2 over that. So let me just put the minus 2 in the front. And then I will write down the inverse Laplace again. And then we have the 1 on the top over s plus 2 squared. Like this, right? So that's what we have. Now, take a look right here. And this is the one, by the way. So think about what the answer is. Just go ahead and just think about it and just say it. What's up? What's the answer for the first one? Well, we kind of did that over there already, right? Okay, so here is the deal. Look at this as just s plus 2 to the first power, so I don't need that. This is the same as s minus negative 2 on the bottom, which is what we did earlier, just that part. So we add that with e to the negative 2t. Yes? Now, for this, it's slightly trickier, so pay close attention to this. We have the minus 2 right here. That's good. Now, we have 1 over s plus 2 squared. It's kind of weird. Don't worry, I got you. Here are some notes for you guys. Note. This time, I will have to write this down for you guys, right? Here, if you have the original Laplace, notice we have s to some power, yeah? So you can expect to use t to some power. Original Laplace of t to the n. This right here is n factorial over over s to the n plus 1 power, right? Good. Now, here is the thing. If you look at this expression in the s world, we have s plus 2 inside. So this is being shifted. So I'm adding the 2 right here. And this is what you have to do. Right here, if we multiply by e to the at, then what's going to happen is that you just do the shiftment in the s world. So look at what the s is right here, and then just go ahead, minus that a value, and then you raise that to the n plus 1 power, like that. So that's one of the properties. So you actually get this right here, s minus a, and then raised to the n plus 1, and then all that stuff. So as you can see, in this case, our n is just nicely equal to 1, yeah? So that's good. On the top, we have 1 already, so that's wonderful. So we will have t to the first power right here. T to the first power, again, n is equal to 1. But then we have the a is negative 2. So just remember to multiply by e to the negative 2. And usually we put down the t first, so that's why I write it down like that. So t to the first and all that. And we're done, so I can erase that. That's it, right? So number 5 right here. All right. So question for you guys. Do you guys remember all your inverse Do you guys remember all your Laplace transform table? Honestly, I don't, because I do a lot, but like I don't, because there are some of the Laplace transforms I think that I haven't done yet. So those are the ones I don't remember, of course, but the ones that I did in the previous video, I do remember that. All right. So number 6. I only have the answer key just to make sure that I can provide the answer key to you guys as well. I want to make sure my answer key is correct, so that's why I'm also having the answer key right here in front of me. Anyway, inverse Laplace of s. Oh man, this is the crazy one. S e to the negative pi over 2 s over s squared plus 1. Okay, so here is the deal. Have a look. This is e to the negative pi over 2s. We are talking about in the s world. The one that we did earlier was in the t world, and I think it's a good idea. Let me just remind you guys the formulas again, right? So here, let me just put this down for you guys one more time. The one that we used earlier is when you have the original Laplace. If you have e to the at power times t to the nth power, look at this part first, which is n factorial over s to the n plus 1, yeah? And then because we have e to the at right here, this tells us we have to subtract a and then raise to the n plus 1. That's the one that we used earlier. However, though, this right here is really confusing. This right here, it's in the s world. So you have to just think about the original Laplace of what function will give you e to the some number times s in the s world. E to the, let me just write it as, this is what? as, like that. So the e to the whatever part is in the wrong world, right? So what is this? You have two answers for this. The first answer is this right here. You can have the delta of t minus a, direct delta function without the t. Yeah. Or another one that you have to keep in mind is if you have the Laplace transform of the unit step function of t minus a, this right here will give you this part, which is e to the as, but then you have to divide it by s. Oops, sorry. Two mistakes so far. The s has been read. Right? So these are the fundamental ones, and just remember that. However, though, this right here is not quite the same as that. So in fact, we have to look at the harder version of all this. One more for you guys. When you have this right here, this is the time that you usually end up with e to the as power. This right here, if you multiply by some function, I'll just put on f, and then if they have the same input, t minus a, like this, then what you do is, this part is the same as that, which is e to the as. But you look at this part, and you just multiply by the Laplace transform of f of t, right? If the inputs right here, they match, this right here is just f of t, like that. And this right here is the general case. This right here, you just take f to be 1, and the Laplace of 1 is just 1 over s, right? All right, so this is the one that we have to focus. And now, this is how you can do it. Whenever you see e to the number times s in the s world, yeah, that's what we have right here. This is telling us that just go ahead and multiply by u, which is the unit step function of t minus whatever that number is. Actually, be really careful. Is this a and that a match, right? If whatever you see, just whatever, okay. You just do t minus. No, sorry. This right here is meant to be negative as, I believe. Negative as. Let me see. Yes, because if it's e to the as, that wouldn't even converge. So it should be negative, and that should be negative, and that should also be negative, right? So anyway, though, right here, this number, just go ahead and subtract. Whenever you see e to the negative pi s right here, you just go ahead and subtract the pi over 2, right? Just like that. All right, so this, again, let me just recall the formulas. Delta, you get e to the negative as. If it's a unit step function, you get e to the negative as over s. And in general, if you have a function and a unit step function, if the inputs are the same, you go ahead and do this. E to the negative as times the Laplace of the function f of t only, right? And this is the one that we're using. Whenever we see e to a number times s in the s world, and notice this is negative as, so the a is pi over 2. So we are just going to multiply unit step function of t minus pi over 2, like that. Right? We are going backwards, and that took care of the first part. Now, we also have to figure out the rest. This is for that. Now, if you focus on the rest, I will just put this down here for you guys. So, note, just put on note. I will write down a lot of notes for you guys in this video. Note, look at the remaining part, which is the inverse Laplace. The remaining part is just s over s squared plus 1. And this right here, it's very nice because this is nicely equal to cosine of t. Right? This is just cosine of t. Well, this right here, if you look at the right-hand side, remember we're taking the inverse, we're looking at the right-hand side, and then look at the inside right here. So in here, this is actually our f of t. Okay? However, when we go back to the t world and put on the answer here, you have to have f of t minus a as well. The input have to match right here. So instead of just put down cosine of t, you actually have to put down cosine of t minus pi over 2, right? So again, this portion is for the f of t minus a. So I'll put this down right here. This is the f of t minus a, and this is the unit step function of the t minus a. So again, we're doing backwards like this. All right, so this right here is the sixth one, like that. I'm sorry, earlier that I forgot the negatives right here, right? So that's number 6, and then now let's see number 7. Yeah, I'm going to erase all this, and yeah. All right, number 7 in action. Here we have the inverse Laplace, and the input is s over s squared plus 2s plus 2. Right? So that's number 7. Again, just want to make sure I'm recording. Good. Now, on the bottom here, s squared plus 2s plus 2. Ask yourself, can we factor it? The answer to that is no, unfortunately not. The worst part is that the bottom right here doesn't even have real roots. So what we have to do is complete the square. So let me do it on the side for you guys. So right here, CTS of this expression, which we have the s squared. Oops, this is meant to be in black. S squared. So s squared plus 2s plus 2. Right? So what you do is you leave it right here and then just add 2 after that. Right? And then what you have to do is the following. Make sure this is the 1 in front of the s squared, which it is. And then look at this number. This number is 2. So what you have to do is take half of this number, which is 2, put it in parentheses and square that, and work that out, which is just equal to 1. So this is the magic number that you have to add and also subtract. Right? So this is the general way to do it. I know some of you guys might be able to just see it and write down the answer. That's fine, of course. But anyway, after you have done this, here you will end up with the first three terms is s plus 1, and then square, and then this is just going to be plus 1. So that's what we have. So that's the first thing. Here we have the inverse Laplace. On the top, we still have the s. So go ahead and write that down. Over on the bottom, we have this, which is s plus 1 square, and then plus 1, which is the same as 1 square, because you know sine and cosine are about to come out. So this is what we have. Good. Now, if this was just s square plus 1, that would be cosine, right? But this right here is s plus 1. So do it really, really carefully. And again, I'll write down some notes right here for you guys. Here are some of the things that you don't know. Again, if this is just s, then you have the following, right? It's just cosine, because we know the original Laplace of cosine t. This is nicely equal to s over s squared plus 1, because the b value right here is just equal to 1. So that's what we have. However, as you can see, we are shifting in the s world. This is s plus 1. So you have to remember, if we multiply by eat, if you eat something, if you eat the cosine t, no, e to the at anyway. If you multiply the cosine t with e to the at, then what you do is look at all the s in the s world, and then you go ahead and shift it, and you do s minus a here and s minus a here. So that's what you have, right? Similarly for sine as well. But here is the thing. This right here matches that a is negative 1. On the top, I don't have the plus 1, right? This is s plus 1. I need to match it so that I can do this, right? So we'll do what we did earlier. Write this down again. So here we have the inverse Laplace. On the top is still s. On the bottom, let me just write it as s plus 1 square plus 1 square. Now, I really want to have the top and this match, so go ahead and just add 1. So that's how you can have the input match, this and that match. But again, as usual, this will change the whole thing. That's no good. It's okay, just go ahead and minus 1. So, as you can see, if you look at the inverse Laplace of this portion, which is s plus 1, if you just look at s plus 1 over s plus 1 square plus 1 square, close that. This is what we can do. And then we can just go ahead and just minus, right? This is a minus, and then we have the inverse Laplace of 1 over this, s plus 1 square plus 1 square, like that, right? So this is actually pretty good now, because we can actually write down the answer for the first one. Again, you see we have s minus a, so this is s plus a has to be negative 1. So what you do is, go ahead and write down e to the negative 1 t, that's a shifting, and then the form is the cosine t. So that's the first one. Next, minus, well, as you can see on the top, this is just 1, there's no s. So this is the sine version, right? And again, for this part right here, it doesn't really matter, because the sign on the top is just a constant multiple, just a 1, right? And this is 1 square, so this and that match already. You know, you end up with sine t, and all you have to do to make the shift in the s world is multiply by e to the negative t. So this right here is it, e to the negative t, all that stuff, right? So that's it. Now, next one takes some space, so I will write it down right here for you guys. So this is a great review if you did the Laplace transform already. Of course, you should also know the inverse Laplace. Now, number 8, right here. Oh, that's delta. No, this is number 8, right? Number 8, we have the Laplace. And this is the inverse, of course. 1 over s to the third power. And then s squared plus 1. Like that. You have 2 ways to do it. First way, you can do, actually you have 3 ways to do it. First way, you can do partial fractions. I will leave that to you guys, because in order to have 1 over s to the third power right here, when you break down, right, the partial fractions, you will have to do a over s to the first power plus b over s to the second plus c over x to the third power. You have to build on a power. And then you add, this is a non-reducible quadratic, so you have to do dx plus e over s squared plus 1. In another word, you have 5 unknowns, a, b, c, d, e. I don't think I want to do that, so let me not do the partial fractions. Second one, you can use the convolution theorem, and integral for that might be manageable, might be okay, but I actually have a convolution idea for you guys later. So let me just give you guys a quick review, right? But let's see. I will just tell you, you can do partial fractions. Right, let me just write down the things that we have. Partial fractions. And again, if you do the partial fractions, the breakdown for this is that you have to first get a, which I don't know, over s plus b over s squared plus c over s third power plus ds plus e over s squared plus 1. Then let's not do that, right? So that's the first way. First. Second, you can use the convolution theorem. And what that says is the following. Notice that we actually have a product inside, namely 1 over s to the third power times 1 over s squared plus 1. And the convolution theorem says the original version is the original Laplace of f of t star. This is the convolution. This right here with g of t, this is going to give you very nice f of s times, this is just a regular multiplication, times g of s. Oops, sorry. S here and s here. So that's good. And of course, you can do it backwards. So to do that backwards, you will do the following. And by the way, let me remind you guys, the convolution is an integral. So this right here, what you do is integral from 0 to t, and then you end up with f of t minus v, g of v, dv. Anyway, if you want to do the convolution for that, it will look like this. Let's write down the inverse Laplace. Look at this as 1 over s to the third power times 1 over s squared plus 1, right? Well, what you can do is you can do the first one, right? You can do the first one. You can break it apart, but inside it's a regular multiplication. On the outside, here it's going to be the convolution because we are going backwards. And then you have the inverse Laplace of 1 over s squared plus 1. And now let's do this in our head. This n is equal to 2. So that means I should have a 2 factorial on the top, but I don't. So I'm going to multiply by 2 factorial, and then go ahead and divide it by 2 factorial. Yeah, good. So this is actually just 1/2. So that's nice. And then this is t squared. That's good. And then you have to do the convolution. So again, you have to convolute it. I don't know if that's a word. And then do this right here, which is going to be sine t. And then you end up with the integral, which is actually 0 to t. This is the f. So you actually have to put t minus v into this right here. So you actually have to do 1/2 t minus v squared, and then regular multiplication inside, and then g of v, which is sine v dv, and then just have to work that out. So yeah, you have to work that out. On the exams though, do not just put down 3 dots. You actually have to work that out and show the teacher what the answer is, right? But this is how you can approach that. I have a better example with the convolution later on. So I'm not going to do the convolution. Not convolution, convolution. This is what we can do. Here is the third way. Let me just write it down right here. So let me just put down the third way right here. Or we're going to use the following, okay? Well, we're dividing by s, huh? So I think there's a formula that we have seen that's dividing s on the outside. That's actually this one right here. If you look at the integral, and if the inside it's an integral, which is the integral going from 0 to t, and let's say we have f of v dv. This right here, if the inside is an integral, then the outside will give you f of s, right? F of s divided by s, like that. In another word, if you take the inverse of this expression, then you just have to do the integral of that. So you see, we actually just divided s 3 times. And this integral is slightly less intimidating than the convolution integral. In fact, this is actually the repeating integral formula. I have a video on that if you want to go check that out. But not to be so intimidating, let me just show you guys how we can do that, right? So here is step 1, right? So this is what we have to do. We know the Laplace inverse of 1 over s squared plus 1. This is nicely equal to sine t. So this is just what we know, right? Then what you can do is the following. Then, right, if you want to do the inverse Laplace of 1 over s squared plus 1, yeah, same one. But if you really want to have an s right here, multiply with that, which is the same as you're just dividing by the s, right? You're just dividing by this additional s. So this s, actually, let me just write it down in red. If you really want to divide it by s right here as well, like that, what you are going to do is this right here, 1 over s, you can just go ahead, look at what this is, and then integrate from 0 to t and change the input to be v. So we have sine v dv, like that. So sometimes it might be a good idea to integrate this little ones more times than do a crazier one. But this is actually not so bad either, because you can just induce integration by parts. In fact, that's a connection between the repeating integral formula versus the this right here, because you have to integrate this 3 times. All right, so with that in mind, just keep that in mind, right? And because I have to erase this now, and I just have to integrate this 3 times. Not so bad though. Maybe you like this more, or maybe you like the convolution, I don't know. But anyway, let's go ahead and do that. Again, 1 over s is you do the integral, so just go ahead and do the integral. Integral of sine is negative cosine, so we have negative cosine v, and then we are going from 0 to t. So be really careful, put t in here first, we get negative cosine t, and then put this right here, we get minus, and this is negative cosine of 0. So in another word, this right here is equal to negative cosine t minus 1, no, plus 1. Yeah? So that's the first one. So in fact, I'm showing you guys this one, right? This is the inverse Laplace. You don't have to do the partial fractions if you don't want to. But anyway, you will see that the next one, the inverse Laplace, if you have the 1 over, if you have the s times s squared plus 1 already, which you know is this, right? Which is just equal to negative cosine phi plus 1. I'm using phi because I will have to integrate that. Well, right here, if you have to divide it by s again, just go ahead, integrate this again from 0 to t. And then you have this in the v world. And just pretty much go ahead and do that. So let's go ahead and do that. Integral of negative cosine is going to be negative sine phi. Integrating this is just plus phi. And then we have to plug in 0 to t. So plugging t, we get negative sine t plus t. Plugging 0 is just minus 0, right? So that's pretty much the answer right here. 0 and 0, so that's just 0. So that's the answer. So the last one here is going to be the inverse. Well, here is 1 over s squared times s squared plus 1. Yep. And then, again, to get the third power, of course, we have to have the 1 over s right here. So this right here, this portion just give you that, which is negative sine phi plus phi. And we have this, so just go ahead and integrate from 0 to t, and then in the phi world, like that. 0, and then this is t, like this. All right, then just go ahead and integrate this. The integral of negative sine phi is going to be positive cosine phi. And then integrating that, we get plus 1/2 phi squared. And then again, plugging, so plugging 0 and t. So in this case, I will actually write it down right here for you guys. This is going to be the following. Plugging t. So first we get cosine t plus 1/2 t squared. This is the first portion, and then minus the second portion. We have cosine 0 plus 1/2 0 squared. Like that, yeah? So finally, you see here is cosine t plus 1/2 t squared, and this is minus 1, right? And that's 0. So finally, the answer is this. Cosine t plus 1/2 t squared minus 1, like that. Yeah, and of course, let me see, 1/2 t squared. Yeah, so just like this. It seems that I make a typo on my answer key. I will have to, because I have answer key right here, right? So 1/2 t squared. I think I actually have the extra cosine t here, which I don't think is correct on my answer key. So let me just get rid of that. And let me just double check, because maybe I did something wrong here, but I don't think so. Yeah, t squared is never multiplied with the cosine, so I think this right here minus 1. Yeah, I think this right here is it. Right? So, yeah, that's it. All right, so that was number 8. All right, now moving on to number 9. Number 9 we have right here. Here we have the inverse Laplace, and we have 1 over. I prepared the s plus 2. I messed up because I didn't want to choose 5, but this is my 5, right? So hopefully this is clear. So this is s, that's 5. But anyway, this one right here. So this right here is different than the one that we did earlier. You don't do partial fraction at all, because this is just a shifting situation, all right? So let's practice this one more time. Just pay attention to the input. Just pretend this is s to the 5th power. In that case, what we need is the following. So again, note, if we have the Laplace of t to the nth power, this will be n factorial over s to the n plus 1 power, right? S to the n plus 1 power. So this is the one that I would keep in mind. However, it's being shifted, right? So again, you have to multiply this by e to the at, and that will be s minus a raised to that power. So that's the idea. So now, right here. Let's just finish this right here. We can see n has to be 4, but I don't have 4 factorial on the top. It's okay. Let's just go ahead and multiply by 4 factorial, and just don't forget to divide it by 4 factorial all the way on the outside. Now let's write that down. 1 over 4 factorial, that's the same as 1 over 24. And then for this part, of course, we know we will just go back. So that's t to the 4th power. Let's write that down first, t to the 4th power. And then a is -2. So just put that right here. So we have this and then e to the -2 t, like that, right? So sometimes you do partial fractions, sometimes you just have to remember this formula. This is, of course, just kind of, yeah, this is the one that should not be forgotten. Yeah. All right. Number 10. Though this is the fun one, we have the inverse Laplace of 1 over square root of s plus 1 over square root of e to the s. Yes. How can we do this? Well, this right here, it's the same as Laplace of t to some power, right? So let me just remind you guys, this right here again, and this is not shifting, so I don't have to worry about the e to the at part. This is just going to be the following. So note, the original Laplace of t to the nth power, this right here is equal to n factorial over, and we have s to the n plus 1, right? So in this case, you can just go ahead and write this down. Here we have the inverse Laplace. For the first part, we can look at it as 1 over s to the 1/2 power. So we can use this to take care of the first one, yeah? N plus 1 has to be 1/2. So n is equal to what? N plus 1 is equal to 1/2. So n is actually -1/2, right? But on the top, I do not have -1/2 factorial. It's okay. Let's just go ahead and do the same thing. Let's go ahead, multiply the top by -1/2 factorial. And then on the outside, just remember to divide it by -1/2 factorial, right? And you might be even wondering that what in the world is -1/2 factorial? Because this formula right here, it's only good for 0, 1, 2, 3, 4, 5, and so on for the n, right? However, if you extend the concept of the n factorial, this right here is the same as saying gamma of n plus 1 over s to the n plus 1 power, like this. And if you want to have -1 over 2 factorial, you can just put that right here into n, and you can just put that right here into n. So I will just have to tell you right here. Gamma of, let's see, let me just write it down like this. -1/2 factorial. This right here, it's the same as you put -1/2 right here, which is the gamma of -1/2 plus 1, like this. And then you can watch my previous video and all that stuff. This right here is gamma of +1/2, and you end up with a nice number. It's just square root of pi. And again, what exactly is this though? You have to remember this right here, it's actually an integral. So I will actually just remind you guys if you are interested to work that out from scratch. This is the integral going from 0 to infinity, and you actually have to do t to the 1/2 power, which is 1/2 power right here, right? T to the 1/2 power, and then, oh, sorry, 1/2 power minus 1, because I'm looking at the gamma function. So this right here, yeah, and then e to the -t, and then we have dt, like that. Yeah, so if you work that out, you actually end up with square root of pi. So this right here is actually just square root of pi, so is that. So just keep that in mind. Pretty crazy stuff, I know. Okay, however, what's the second one though? For the second one, this is just the inverse Laplace, and we can do some exponent business. The square root is the same as 1/2 power. E to the s to the 1/2, it's the same as e to the 1/2 s. In the denominator, we can bring that up. So this becomes e to the negative 1/2 s. Right? Again, square root in the denominator, that's how we get negative 1/2, and then with this, like that. Well, this right here is almost done. This right here, we have to remember the delta function. Remember, when we have the inverse, when we have the original, let me write down the original. When we have the original Laplace of delta t minus a, this right here gives you e to the negative as. Very, very nice, right? So you just have to go backwards. Now we are all done. Let me just write down the answer. Here is 1 over square root of pi. Good stuff, huh? Now here again, the n was let me just write this. N is equal to negative 1/2. Yeah, the n was negative 1/2, so this is the same as t to the negative 1/2 power. Done. Actually, let me just put this down here. The n was. Let me have this because we want this to be that, right? So that's why I wrote down earlier. Is equal to 1/2, so that means n is equal to negative 1/2. So that's how we get the negative 1/2 right here. For this, a is 1/2, so you just put it right here. So you just have to add the delta of t minus 1/2, like this. And if you want to be fancy, you can put this down, join that. So finally, you have 1 over square root of pi t, and then plus delta of t minus 1/2. Just like that. Cool, huh? Yeah, so have a look, have a look, have a look. All right, that was number 10, and of course we are moving to 11 right here. Number 11. And as you guys all know, I dropped the cap and I'm not going to pick it up. Number 11 is face. Okay, inverse Laplace of s plus 8, s plus 8 over, on the bottom here we have s squared plus 4s plus 13. Let's see. Always ask yourself, can we factor the denominator? In this case, unfortunately, not. So let's try to complete a square, and that's actually how we have to do it. So let's do this in your head, right? This time it shouldn't be too bad. This right here is just s squared plus 4s, and this is 1, that's good, and this is 4. Take half of that is 2, square that is 4, so I should have the f4 right here. But originally it was 13. 13 is the same as 4 plus 9, so this is just like this. Yeah, so of course, the first part, completing the square is done, so I'll write it down right here for you guys. Here we have the inverse Laplace. And on the bottom here, we have this. On the bottom here, we have s plus 2 squared, so s is in red. S plus 2 squared plus 9, which is the same as 3 squared. Yep. And then, let me still write it down the top, which is s plus 8. S plus 8. Nothing changed on the top. Actually, I'm not going to put on plus 8. Plus 8 is not nice. Why? Because here we have s plus 2. So I really want to have an s plus 2 on the top, right? Here is s plus 8. So I'm going to write it as s plus 2, and then of course we all know 8 is the same as 2 plus 6. So this is how we are going to break down. This over the denominator and that over the denominator, right? So I will write it down one more time for you guys. Here is the inverse Laplace. This over that, which is s plus 2 over parentheses s plus 2 square plus 3 square. Very nice. And then right here, we will add 6 is a constant multiple. We'll put that outside. 6 inverse Laplace. And then we just have a 1 on the top. And then here we have the s plus 2 square plus 3 square like this. Okay, remember, this is being shifted. Originally, it would be a cosine situation, right? But it's being shifted, so this is what we do. First, you see that this right here, it's going to be cosine of 3t, right? Imagine this and that just an input, like maybe like a bigger s or so. This right here, you will get cosine of 3t, but it's being shifted, and then a right here is negative 2. So you have to remember to multiply by e to the negative 2t, like that. Now, for this one, well, this is not so ready yet, because on the top here, it's just 1. I really want to see what? I really want to see a 3. Now 3 factorial is just 3, because this is the sign situation. It's b over something square, right? The function square plus the same number square. So I really want to see the 3. Well, I multiplied it by the 3, but just remember to divide it by 3, right? So you will see that this is actually plus, this and that's 2. And this portion now is just the sign version, so it's sine of 3t. And then we have to do what we did over there, right? Of course. So just multiply by e to the negative 2t. And then we are done. I'm not going to ask you guys, do we need to put on a plus like 20 something more times? So yeah, that's it, huh? All right. Okay. Now for the next one, it's a crazier partial fraction one. So it's a lot of algebra, and you just have to be patient. If you guys don't know already, to do differential equations, you have to have a lot of patience. And also, especially linear algebra, you have to have tremendous amount of patience. All right, number 12, right here. Inverse Laplace of 1 over s to the fourth power plus, and I'm very sorry I had to do this. This is 5, and then s square, and then plus 4, right? And then, no, there's no ds. This is just like this. All right. We can factor out the bottom. That's nice. If we do so, this is going to be, let's see, treat this as, quadratic. You get s square plus 1 times s square plus 4. Yeah? And it works. Now, again, you have the convolution way to do it. If you prefer to do the integration by parts and just do the integral, you can really do the convolution. But this one, let me show you guys the partial fractions. Let me just show you guys a partial fraction for this. So, partial fractions in action. Right, this right here is the partial fraction. My F doesn't look nice. Like this. Yeah, slightly better. Anyway, here we go. This is 1 over, and we have s squared plus 1, s squared plus 4. And we have to break down into 2 parts. So the first one is going to be s squared plus 1. But the thing is that this is an irreducible quadratic. On the top, we must have as plus b, namely a linear. Similarly, the second one is an irreducible quadratic. So on the top, we have to have cs plus d. Crazy stuff. Now, clean the fractions, so multiply everybody by this and that. And then let me just go ahead and do that. Right? Just multiply everybody by that. So you actually end up with 1. And let me put on 1 right here. and that's equal to this times that pretty much. So we have as plus b times s squared plus 4 plus cs plus d times s squared plus 1, right? And then the deal is that just multiply this out and hope for the best. You end up with a 4x4 maybe system of equations. So unfortunately, cover up doesn't work because you cannot cover up and then make a term, a factor equal to 0, unless you want to use complex numbers, but don't. You could, let me know, but not now. Anyway, so here, multiply this and that, we get as cubed. And the truth is, I didn't work this out beforehand, so I'll just see. Anyway, as cubed, and then this times that is plus 4as, and then this times that is plus bs squared, and then plus 4b. And then, let me write down this below. So this is going to be cs cubed. So we add cs cubed plus this and that, which is cs, and then plus this and that is ds squared plus, lastly we have plus d, like this, right? So now let's just combine terms and all that stuff. So you can see we have the a plus c, and then the s third power plus, let's write this down next, which is b plus d, and then s squared, and then plus 4a plus c, and then s, and then lastly we have the 4b plus d. It's a constant, right? And of course you can see that we have the 1, 1, 1 and all that stuff. Now, what that means is that we must have this right here equal to 0 because the left hand side doesn't have the s to the third power. So we must have a plus c equal to 0. Likewise, we also need to have b plus d equal to 0. Likewise, we also have to have 4a plus c equal to 0. And then we also need to have 4d plus d equal to, this is the constant, so we actually have to have it equal to 1, right? Now, if you see it, it might be, 4 by 4, but it's actually pretty nice because this and that, well, if you just look at these two equations, they only have a and c. So from here you can see that c is the same as negative a, and then you can just do it. So you can put this right here. So that means 4a, right? 4a minus a is equal to 0, and of course a is equal to 0, right? That should be pretty clear. Likewise, this right here tells you c is equal to 0. Man, it's weird. Now, have a look here. This right here tells you d is equal to negative b, and this right here will tell you 4b, and then d is negative b, so minus b right here. Right? This is this part. Minus b has to finally equal to a number. So you see, here we have 3b is equal to 1. Oh, shout out to 3 blue, 1 brown. Look at that. And then this is equal to b is equal to 1/3. b is equal to 1/3. That means d is equal to negative 1/3. Not so bad, okay? Not so bad, you guys. All right, so a is 0, and this is 0, so this is out, and all that stuff. So let me just write it down. This is 0, b is 1/3, c is 0, and this is positive 1/3, right? So some pretty long partial fractions. Now come back here and let's go ahead and do the inverse Laplace. Well, let's do the first one, which is just 1/3 over s to the second power plus 1. 1/3 on the top. S squared plus 1, right? And if you would like to close that, and then the second fraction is this, which we just add inverse Laplace. That's a horrible inverse. That's a horrible also. Plus the inverse Laplace. We have a 1/3, yeah? So we can actually put that in the front, right here. And wait, 1 is negative. This right here is the negative 1. D is negative 1, yeah? Negative 1/3. So this is technically minus 1/3, yeah? And you can see that that's meant to be a negative 1/3. And then we have that over the s squared plus 4. So already as s squared plus 2 squared, like that. On top is 1. All right, as usual, perhaps I should guess my secret weapon. Yes, I found my green pen. This right here is pretty nice to do. This right here is not. On the top, I need to have a 2 because this is a 2. So I need to multiply by 2 and then divide it by 2, like that. Yeah? All right, so if you would like, you can put a 1/3 in the front for the first one. So that's already done like this. 1, and then the 1/3 all the way in the front, if that kind of bothers you. All right, now here we go. Finally, here's the answer. All right, here is the answer. 1/3. This right here is the sign, right? So this is the sign, and then the b value is t1, so just sine t. Next, this and that is minus 1/6, and then we have sine of 2t, just like that. Done. All right, ladies and gentlemen, some partial fractions business. It's not so bad if you just kind of do it quickly and all that stuff, and then yeah, things like this. If you would like, you can also do the convolution theorem, as I said. Anyway, that's it. So halfway done. Halfway done. All right, now number 13, right here. Inverse Laplace of 1 over s to the 4th power e to the 10 s power. Now, as you can see, we have the e to the some number s. Yeah? This is what we have to do. First, let me just rewrite this for you guys. This right here is the inverse Laplace, and then this right here is e to the negative 10 s over s to the 4th power, like this, right? And now this is what you can do if you don't want to just write down the formula every single time. Here is how you can do it in your head, right? Whenever you see e to the negative 10 s, a number s, you have to get the unit step function ready when you go back to the t world. So to do that, let's just go ahead and put that down right here all the way at the end. When you have e to the negative 10s, you actually have to have u of t minus this right here is the a, right? It's negative as, right? For that. So it's t minus 10. It's pretty much whatever you see is whatever you get right here, yeah? Like this, yeah. You always have to have that. And then what you need to do is you have to figure out the f of t, right? F of little t. Well, let me just write it down right here. The inverse Laplace. If we didn't have, if we didn't have this, it's just 1 over s to the 4th power. All right, our n right here is 3, so I need to have a 3 factorial on the top. So let's go ahead, multiply the top by 3 factorial and divide the bottom by 3 factorial. Top and bottom 3 factorial, right? So we end up with 1 over 6 t to the 3rd power. So that's how you will get originally. This right here is our f of t. But when we go back, we have to have f of t minus 10. The input have to be the same. So this right here has to be f of t minus 10. And all you have to do is, instead of the t, you write it as t minus 10. So finally, 1 over 6 t minus 10, and then to the 3rd power, just like that. Yeah, so that's it. That's it. So I think this is the easiest way to do it. Just have to remember the formula that we are using in this case is when you have the Laplace transform of f of t minus v, unit step function of the same input, t minus a, not t minus v, t minus a. Same thing, doesn't really matter, just some variables. This right here gives you e to the negative as, and then you have the Laplace transform of the f of t. So you just have to multiply by this guy. So that's the deal right there, right? I'll try not to use screen, not anything against screen, but like, just like that. All right, so that's pretty much it. Now, next, number 14. This one, we have inverse Laplace of inverse tangent, inverse Laplace of inverse tangent of 1 over s. Weird. This is not from table right away, huh? Actually, there is an entry that gives you this, but I will show you guys how you can actually work it out from scratch, right? So suppose you didn't do the one that I demonstrated for equation number something in the previous video. So, how can we do this though? In fact, we don't know this too well. But if we differentiate this, it's actually not so bad, because the derivative of inverse tangent is actually going to give you a rational expression in the s world. For example, the derivative of inverse tangent is 1 over s squared plus 1, right? And then, of course, we just have to work out our usual derivative, all that stuff, and that's going to make it work very nicely. So you can go ahead and do the derivative, but before I do the derivative, let me first tell you, this expression, inverse tangent of 1 over s, this is actually nicely equal to, and again, we still have the inverse tangent, but this expression is actually the same as inverse cotangent. Right? This right here is actually the same as inverse cotangent. And people might be worried about the domain and all that stuff. Let me see. All right, so this right here, it's the same as inverse cotangent of s. Yeah, okay. And again, some people might be defining the inverse cotangent to be some other things, but just different branch. But usually this is okay, right? Because don't want to be too bizarre with like the domain and the range of all that stuff. All right, so you can do it like that. And again, if you have the inverse cotangent, sorry, not minus, just cotangent. This right here is the same as cotangent of s. Sorry, let me do it again. Inverse tangent of 1 over s, this right here is the same as inverse cotangent of s, right? And again, you can just go ahead and approach it this way, but you can also do it like this. This right here is also the same as pi over 2. This is the cofunction identities, but it's the inverse version of that. So this is the same as saying pi over 2 minus inverse tangent of s. Maybe you guys will be familiar with this expression slightly more than this or that, right? And later on, I'll be doing the trig identity proofs marathon. Yeah. All right, anyway, whichever expression you want to look at, as long as you know how to do the derivative, you are good to go. Now, here is what I want you guys to remember. So this is the one that we have to use, right? Note. What's the difference between note and use? Well, same thing. I don't know. All right, here's the deal. When you have the, let me write it down like this. Inverse, when you have the Laplace transform of a function, that's the f of t. This right here, we know is f of s. Yeah, it's f of s. No problem on that. However, sometimes, if you have this multiplied by just t, in that case, what you do is, in the s world, you differentiate this with respect to s, and then you multiply by negative, like that, right? Well, from this right here, in fact, I will have to tell you, this only works precisely if f of s approaches 0 when s goes to infinity. So this is just some little note for you guys. Because, in fact, mu prime f showed me a counterexample. If I don't have this condition, then this is not entirely true, right? But with this condition, this is true. And I will have that video in the description for you guys. And that's actually how I met mu prime math for the first time. So this right here, I will just tell you to see mu prime math video. Right? Link will be in the description for your convenience. All right, now what we'll do is take the inverse on both sides, and you will see that the left-hand side is just t f of t equals, this is negative d ds, and then we have f of s, right? And then you see I don't have the Laplace anymore because I will say this right here, and then we do the inverse right here. So that's a formula to get back to the f. But I have little t, so it's okay though. Have a look. F of t, this right here is just divide the t on both sides, so we have 1 over t, and then we have the inverse Laplace. And then you multiply by negative here. Let's put a negative on the outside, yeah? So the negative on the outside. And then you just do the derivative in the S world. And then you have a better experience with inverse Laplace. So this is a very nice formula, right? Very nice formula. No, this is not the answer. We haven't done it yet. Here we go, right? So this is how we are going to do it. To get the inverse Laplace of this, right? As I said earlier, this expression is the same as that. It's the same as that. And then let me use this version. So this is the inverse Laplace of pi over 2. Yeah, let me just write it in black. Pi over 2 minus inverse tangent of s. All right? Good. Now, remember this right here will give you f of t. This right here will also give you f of t. So this is the following, right? This right here, what we'll do is multiply by negative 1 over t. So we have the negative 1 over t first, right? And then we still have the inverse Laplace here. But what we'll do is, inside here, I'm going to differentiate it in the S world. And then we have all that inside. So pi over 2 minus inverse tangent of S, like this. So again, the idea is that if this expression is too bizarre, go ahead, differentiate it, and then multiply by negative 1 over t. That will still give you an answer for it. Still give you the answer for it. Now let's see if this is really any good or not. Here in the front is negative 1 over t, and then do the inverse Laplace. Inside here, well, the derivative of this is just 0. The derivative of this right here is actually negative. Right, this is negative, and then we have 1 over, this is s squared plus 1. S squared plus 1, like that. And again, the truth is, if you differentiate this right here, differentiate that right here, and differentiate this right here, they are all the same derivative. Yeah. And again, I'll show you guys the proofs later on. All right, now we can put a negative on the outside, so you actually get positive 1 over t now, and then the inverse of this right here is just what? Sine t, isn't it? Again, negative becomes positive already, so that's it. This right here, finally, just give you, let's write it down in the classic way, sine t over t, just like that. Very, very, very cool, right? Have a look, have a look, have a look. Dun, 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 dun. I have another example for you guys because I know this right here might be super bizarre sometimes. So here is another one. Number 20. No, why is that? No, I thought that was number 19. I was like, wow, I'm almost done. No, number 15. So, inverse Laplace. Here we have ln parentheses, ln parentheses, and then we have the s. Let me write it down better. Number 15. inverse Laplace of ln s squared plus 9 over s squared plus 1. Okay, here's the deal. If we differentiate ln, again we will end up with a rational expression, so that's good. We prefer that. If you notice, all the Laplace pretty much just in terms of s, right? In terms of s in the s world, obviously, as a rational expression in the s world. There we go. So differentiation first is a good idea. So I'm going to differentiate the inside first, and then just make sure on the outside we multiply by negative 1 over t. So here is how we are going to do it. Multiply by negative 1 over t, and then here we have the inverse Laplace, and then the inside we are going to differentiate this with respect to s, and then this expression right here. Now we are about to take the derivative. My suggestion is use natural log property. So I will write this down as ln of s squared plus 9, and then minus ln of s squared plus 1. Right? So that's what we have. And then I will close that, and then I will close this. So that's pretty much the work that we have to do. So again, we're using this property right here. And the real quick check is that I forgot to mention, we should always check this. F of s is approaching 0, is it? Well, if you take s to be infinity, the inside will be approaching 1. Yeah, good. ln 1 is 0, so this works. Earlier, if you put s to be infinity, inverse tangent of 1 over infinity is inverse tangent of 1 over 0, inverse tangent of 0, which is 0, so again, this works. Yeah, so just check the limit and all that stuff. Anyway though, let's go ahead and do the derivative. Here is negative 1 over t, and then we still have the inverse Laplace inside out. So differentiate this. Finally, we can use the chain rule, yeah? Derivative of this is 1 over s squared plus 9, but the chain rule says we have to multiply by the derivative on the top. So we get 2s. Yeah, we get 2s, like that, derivative of the top. Minus the derivative of this is s squared plus 1 on the bottom. And again, we have to use the chain rule, so the derivative of the inside is also 2s. So let me just put a 2 in blue. Why? I don't know. Just do like this. Yeah, the chain rule in action, and again, I think all my s are in red so far, so that's good. And then this right here. Seriously, otherwise that would totally look like a 25. That's not good, so that's what we have. Okay, now we just have to do the inverse Laplace of this and the inverse Laplace of that, and that's it. Notice this is going to be the cosine version, isn't it? Very nice. For the 9, of course, you look at this as 3 squared. On the top is s, and this is s squared, so that match already. We don't need the s forever, right? We don't need to do anything. And of course, this is a 2 and all that stuff. So here we go. We have the negative 1 over t all the way in the front. Put down parentheses for the result of the inverse Laplace. 2 is 2, so perhaps I'll write that down. Why not? And then s over s squared plus 3 squared, that's going to be cosine of 3t, like that. Very good. Minus 2 is another 2 right here. This is just cosine t. Done. Yeah. And then distribute if you would like. And yeah, so you get negative 2 cosine 3t plus 2 cosine t all over t, like that. And we are done, like this. All right, so that's it. So sometimes if Laplace transform gives you some trouble, inverse Laplace transform gives you trouble, differentiate the inside first and then just multiply by negative 1 over t, like that. All right, so that's the idea. And you might be thinking, can we integrate the inside first? Yes, and an example is coming up pretty soon. So let me erase this right here first though. How many of you guys are taking differential equation this semester? If so, let me know, right? In fact, I am not teaching differential equations. I'm sorry, Brett. I'm sorry, Brian. I'm sorry, Eddie. Yeah. Those were my former Cal 2 students. And hopefully everybody is doing well, including you guys who are watching the videos right now. All right, number 16. Number 16. Inverse Laplace of 1 over s squared minus 16, like that. Oh, it's just a coincidence. 16, 16. I didn't prepare that. Actually, it's not. That's to make a harder one. Of course, s to the fourth power, right? Otherwise, the partial fraction will be too easy. S to the fourth power, right? Now, factor things out. Can we do this in your head? Let's just go ahead and do this in your head. Actually, no. Let's do this in our head. We first get s squared minus 4, and then s squared plus 4. And for the s squared minus 4, we can do that as s minus 2, s plus 2, and then the s squared plus 4, unfortunately, cannot be factored in, so that's what we have. For this one, I will show you guys partial fraction for it. So here we go. We have 1 over s minus 2, s minus x plus 2, and then s squared plus 4. Right? This is not so bad. Now check this out. First, we have to have a number over s minus 2, and then another number over s plus 2. Linear, so on the top it's just numbers. Lastly, we must have a quadratic, right? Quadratic over s squared plus 4, like this. So I will just call this to be A, B, linear on the top, so it's CS plus D. All right? Now, let's do the cover up method, and let's do the cover up in our head, because cover up is so Cal 2. Differential equation is the cover up in your head. So have a look here. To figure out what A is, go back to the original. You cover out the same denominator. And how are you going to make s minus 2 equal to 0? S has to be 2, right? 2. Put 2 here and put 2 here. 2 plus 2 is 4. This is going to be 4 plus 4, which is, I almost wanted to say 16. No, this is 8, and this is 4. So 8 times 4 is 32. So A is 1 over 32. Now, to figure out B, cover this up, and you let s equal to negative 2. Negative 2, negative 2. This is negative 4, and that's still 8. So we get negative 1 over 32. Right? So far, so good, huh? Now, my recommendation to figure out the C and D is just do the usual way. Or if you would like, you can plug in s is equal to 0 or s is equal to 1. Any s value that you haven't used yet, that's fine, and you work out its equations. But again, my experience is just to suggest as let's multiply everybody by the lowest common denominator, which is the s minus 2, s plus 2, and then s squared plus 4. All the stuff. And then work out the algebra. All right, the left-hand side, we have 1. And then this right here is 1 over 32. This is going to be slightly bizarre because we have a lot of fractions. All right, this times that, the s will be also, we have this, which is s plus 2, s squared plus 4. Right? Next, minus 1 over 32. S plus 2 will cancel, so we have s minus 2, s squared plus 4. That one, that, so we have plus cs plus d, and just this and that, so it's, just this, which is s minus 2, s plus 2, like all this. just work that out real quick. So here is 1 over 32. This and that is s to the third power plus 4s, and then plus 2s square, and then plus 8. Am I right? Yes. And then the next part is minus 1 over 32 times pretty much the same thing, huh? So we get s third power plus 4s, and then minus 2s squared minus 8. Yeah? And lastly, I will actually, can we do have some more space? Like this, and then lastly, I'll just put on plus. This is, I will multiply this out, yeah? So we get cs plus d times s squared minus 4. Can we see? Yes, okay, you guys can see this right here, yeah. All right, now the bizarre part is just, again, just multiply this out. So we get, nothing can be reduced. This right here, 1 over 32 s third power. Actually, I don't need to have too many, oh, actually I do. 1 over 32. Why is this so hard? I don't know. Anyway, 1 over 32 s to the third power, and then this times that is plus 1 over 8 s plus 1 over 16 s squared plus 1 over 4. Good. Now I have some minus going on, so it's minus, and this and that is 1 over 32 s third power minus 1 over 8 s, and then minus 1 over 16 s squared, and then minus 1 over 4. Sorry, minus minus should be a plus, minus minus should be a plus, and that's it. Lastly though, I have to multiply this out, yeah? So this times this, I just pretty much go ahead and do that. So cs, so we still have the plus cs third power plus cs times negative 4 is negative 4 cs, yes, and then plus ds squared, and then lastly we have the minus 4d, like all this. Oh my god. All right, I just need to figure out what c and these are, yeah? So let's see, do we have the constant terms? We do. Here is the constant term, and here is the constant term, and here is the constant term, right? Yes. So based on this, we can conclude that the constant term has to be equal to 1. Therefore, we know 1 over 4 plus 1 over 4 plus negative 4d, so it's just minus 4d. This right here should be equal to 1. Work that out. This is 1/2. Put it to the other side. Negative 4d is equal to negative 1/2. D is equal to positive 1 over 8. So hopefully this is right. I don't know because I didn't write that down. I only have the final answer. So I hope this is right. D is equal to 1 over 8. Now how about C? Where's C? Okay. Okay, with the S. Yeah. So let's see. Here is the one with S. Here is the one with S. And here is the one with S. So this implies the coefficients, we have 1 over 8 minus 1 over 8, and then minus 4c. This right here, there's no s on the left-hand side, so it has to be equal to 0. This is 0, so negative 4c is equal to 0. C has to be equal to 0. Okay, done. C is 0, D is 1 over 8. Whew. All right, now come back here and then do the inverse Laplace. Inverse Laplace. First fraction, we have the 1 over 32. Let me just write it down like, let me see if I don't even have enough space for that. 1 over 32, let me just put that in the front, I guess. So here we go. Do the inverse Laplace of this, which is 1 over 32 all the way in the front first. And then inverse Laplace of 1 over s minus 2. So that's good. And then just continue. The next part is minus 1 over 32. So we have the minus 1 over 32. And then the inverse Laplace of 1 over s plus 2. And lastly, this is out, so we have 1 over 8 and all that. So we have to add 1 over 8. And we have to add 1 over 8 inverse Laplace of a number which is just 1 because I put a 1 over 8 in the front already. And that's s squared plus 2 squared, like so. Right? Now, finally, we'll see. This right here is just 1 over 32. Good. This right here is e to the 2t. Good. E to the 2t. Remember, it's s minus a, and then it's e to the at. Eat. Right? Then minus 1 over 32. And then this is e to the negative 2t for the second one. Lastly, though, well, this is the signed version, and as you can see, this right here, we have a 2. So we need to have a 2 right here, and that means we have to divide it by 2 here. So it's just like that. Therefore, we actually get 1 over 16 on the outside, and then we have the sine of 2t. Whew, took a while. And, uh-oh, I have the minus plus. Okay, it's d negative or positive? Oh, I'm sorry. D is negative. Have a look, because this is 1/2. So this right here is 1, and this should be a 1/2, yeah? Because 1/2 minus, so it should be 1/2. And then divide, so D should be negative 1 over 8. So D right here should be a negative 1 over 8, and C doesn't matter, it's 0 anyway. So this right here should have been a negative 1 over 8. And then this right here should have been minus 1 over 16, and then all that. So, ooh. Yeah, just like this. All right, done. So have a look, have a look, have a look. All right, so I have to erase all that, yeah? And now, remember this equation here, this is the inverse Laplace of 1 over x to the 4th power minus 16, huh? Right? That was what we just did. Now, number 17, I will put it down here. And we have this right here, which is the inverse Laplace. And we have s to the 3rd power, s to the 3rd power over s to the 4th power minus 60. Ah, again? Huh, okay, and this time square. Well, do I want to do the partial fraction again? I don't think so. But if you look at this and look at that, what's the connection? Depends on how you look at it. Eh? If you differentiate this, the function part will give you that. Or you can also look at this as, if you integrate this, the function part will be something like this, right? So it depends how you want to look at it. So have a look of the following, right? So I'll tell you guys the answer is actually very, very simple, but I will explain that to you guys. In fact, we can make good use of this for this question. That's why I haven't erased that down yet. All right. So recall, this is the one that we're actually going to use. When we have the Laplace, and this is the original, Laplace of f of t, this right here is just, okay, look at what the f of s is, yeah? Just like that. And if you multiply this by t, all you have to do is differentiate this with respect to s, and then you multiply by a negative. So that's pretty much it. Now, of course, again, this is only true if f of s goes to, actually, this is true. But the next one is not the one that I have to tell you. This is the one I have to tell you. I can take the inverse on both sides, and that means I can put this to the other side. I will tell you, let's do it like this. If you have t, f of t, this right here, I can say it's the same as saying, put the negative to here, and then I will do the inverse Laplace of this expression, which is dds of f of s. This is true. So that's exactly what we have to do. And again, this is true if f of s is approaching 0 when s is going to infinity. Right? Now, how are we going to make use of that though? Just look at this. So, from this we know that this is what we know already. So I'll write it down one more time for you guys. We know that the inverse Laplace of 1 over x to the 4th power minus 16. This right here is nicely equal to all that, which is 1 over 32 e to the 2t minus 1 over 32 e to the 2t, negative 2t, and then minus 1 over 16 sine of 2t, right? Okay, let me just see if I can write this down better. Better, maybe. Okay. All right, now what I'm going to do is, right here, for the inside, I'm just going to differentiate this. Oops, not x, s. I'm going to differentiate this with respect to s. Yeah? And if I differentiate this with respect to s, all I have to do is, on the right-hand side, just go ahead and multiply by negative t. Right? Just go ahead and multiply by negative t with the whole expression like that. And that's pretty much it. So, have a look. Let's see. Just write this down. Oops. S. ds, right? Look at this as s to the 4th power minus 16 to the negative 1 power. Yeah? So have a look. The left-hand side is the following. If you do the inverse Laplace, do the derivative first. You bring the power to the front, which is negative and then minus 1. So you have s to the 4th minus 16 to the negative 2. But don't forget the chain rule. So multiply by the derivative inside, which is 4s to the 3rd power. Multiply by 4s to the 3rd power. And that's the chain rule, yeah? So you can differentiate that, and on the right-hand side, I'm not going to multiply anything out. I'll just keep it. This is negative t of all this expression, right? Then, as you can see, this is almost the same as that, except for we have the negative 1 over, we have a negative 4. So all I have to do is just divide both sides by negative 1 over 4. So divide this by just divide it by negative 4. Divide it by negative 4. So this and that will cancel. Finally, I can tell you the inverse of s to the 3rd power over s to the 4th power minus 16 to the 2nd power. This is nicely equal to this. This and that, well, they reduce to positive t over 4. And then all this, you just have to write it down again. So just copy that down. 1 over 32 e 2t minus 1 over 32 e negative 2t, and then minus 1 over 16 sine 2t, like that. And this right here is the answer. Right? This right here is the answer for that. So, pretty good stuff, huh? All you have to do is just recognize the connection between the one that you're doing with the one that you have done already. And usually you will find a lot of good surprise. Very good. Whew. All right, so have a look. All right, good, that page is done, and then just one more page. Check this out, I have differential equations for you guys. That's gonna take a while. Hopefully not so bad. All right, so this is the one I promised with you guys with the convolution. So here we go, number 18. So here we have the, not integral yet, not yet. Here we have the inverse Laplace of 1 over s to the 4th plus 4s squared plus 4, like this. You can factor the bottom, and I'll show you. This right here is in fact the same as the inverse Laplace of 1 over s squared plus 2, and then square, like this. Now, here is the deal. I can look at this as 1 over s squared plus 2 times 1 over x plus 2. Break it apart with convolution instead of the regular multiplication. So here, this is going to be the inverse Laplace of 1 over s squared plus 2, convoluted with the inverse Laplace of 1 over s squared plus 2, like this and like that, right? And actually, let me just rewrite it so I have more space for the other stuff. So sorry, 1 over s squared plus 2, convolution, inverse Laplace of 1 over s squared plus 2, right? What's this? Sign of something, right? I didn't put on just one, just to give you guys some more flavor. This is the same as square root of 2 square. So on the top, I need to have the square root of 2. Likewise, divided by that, same thing, square root of 2, and then divided by that. So for the first one, we actually end up with 1 over square root of 2 sine of square root of 2t. And you have to do the convolution of 1 over square root of 2 sine of square root of 2 t, like this. Now, here we go. This is the convolution formula. First, constant, well, actually, let me just say this right here is my f of t. And this is just f of t. And now say this right here is the g of t. Right? So, the convolution formula says you actually end up with the integral going from 0 to t. And you write down f of, right? So let's write down the f first, which is 1 over square root of 2 sine of square root of 2. You write down f of t minus phi. So this t right here actually becomes t minus phi, like that. So this is actually the f of t minus phi. This is the first part. And then for the second part, you actually have a nice one. Again, this is our g of t. When you put it inside here, you just write down g of phi. So you just have to change the t to phi. So you actually end up 1 over square root of 2 sine of square root of 2 phi, like this. One thing here is that inside is just a regular multiplication. And we are in the phi world, so be really careful with that. Now, here is the deal. Cleaning things up before we do the work. Here, 1 over square root of 2, 1 over square root of 2. Multiply, put it outside, so we actually get 1 over 2. And then just to show you guys purple, this is the purple 1 over square root, 1 over 2. Anyway, here we have integral from 0 to t, and this is sine of, distribute that, square root of 2t minus square root of 2 phi. And then times sine of square root of 2 phi, like so. Yeah. Now you might be wondering how in the world can we integrate that? This is the square root of 2. Can you guys see? I just realized there's a glare. Maybe. How can I block that? Like this? A little bit. better, a little bit. Right, I'm sorry for the lighting. Anyway, we have to integrate this guy right here in the phi world, but the thing is that, you can use integration by parts. Well, what else are we going to do? Identities, and that's the one we're going to do. So here is the deal. I will write this down here for you guys. So let's call this to be alpha, or just capital A, because why not? And this is B. Sine A times sine B is equal to the following. I'll just write this down here for you guys. This right here is equal to 1/2 cosine of A minus B. And then you minus, right? Minus. And you have cosine of A plus B, like this. Like that, right? So sine A times sine B is equal to cosine cosine, and then this right here is minus and all that stuff, right? Now, just worked out the integral, and that will be it. So we have the 1/2. Multiply with that, so we'll end up with 1/4 all the way in the front. Integral from 0 to t, I'm sorry. And then the first one, we will get cosine of, we have to do A minus B, so it's going to be square root of 2t minus square root of 2 phi minus B, which is that, square root of 2 phi, right? So that's the first part, and then we have to minus, and again I factor out the 2 already, 1/2 already. And the next part is cosine of, and you just add cosine of A plus B, which is square root of 2t minus square root of 2 phi plus square root of 2 phi, like this. All right, d phi. Now, all the way in the front, we have 1/4. So this is integral from 0 to t, and this is cosine. This and that can be combined, so we have square root of 2t minus 2 square root of 2 phi, and this and that can be cancelled. So we get minus cosine square root of 2t d phi. We are ready to integrate. So here we go. We have the 1/4 in the front. Put down the parentheses for the result of the integration. Integral of cosine is positive sign, so that's good. So we have the positive sign right here. And the input is the same, so let me just stay. Square root of 2t minus 2 square root of 2 phi. And the reason we can do this is because inside it's linear. But when you do this, don't forget to do the Lu chain, namely the reverse chain rule. We are in the phi world, so the derivative of this part is this. So divided by that, so I will put down 1/-2 square root of 2, like that, right? So that's the antiderivative of that. For the second one, though, it's trickier because you have t right here. However, we are in the phi world. So all you have to do for this is just write down minus cosine of square root of t, square root of 2t, and then you just multiply this by phi, because again, we are in the phi world. So that's pretty much it. Now, we just have to plug in. So, let's see. We have 1/4 all the way in the front. Man, let me see how should I. We have the 1/4 all the way in the front. Okay. Plugging t into phi, right? Plugging t into phi. So first part we get, I'll put this down in blue, I would say. Yeah. Let's put this down in from 0 to t. Put this down into blue. So this part is let's just do it in black. Sorry. Anyway, go. This is positive 1/-2 square root of 2. And then plugging t into phi, so we have sine of square root of 2t minus 2 square root of 2. This becomes t now, so that's good. And then we have minus cosine square root of 2t. And again, this is a t now, right? So that's the first part. And then we have to plug in 0, so we have to minus, plug in 0, so we get 1/-2 square root of 2 sine square root of 2t minus 2 square root of 2 times 0, and then minus cosine square root of 2t times 0. Right? So it has two expressions inside. Now finally, we have the 1 over 4, and let's do the blue pen to simplify. We will see this and that is equal to negative, right? This and that can be combined as negative square root of 2t. So that's good. This is just that, doesn't really do much. This is out, this is out, right? Now, here's the deal though. Here is negative, yeah? Instead of the sign. But sign is an odd function, so we can put this on the outside. So the first part is going to be positive. So we get positive 1 over 2 square root of 2, and then we have sine of square root of 2t. Yes. And then this is minus cosine square root of 2 t and t. And usually we could put down a t first. So let me put down this t first, make it slightly more clear. And then for this part, it's just minus minus, so it's plus. So we just add, right? Again, just add 1 over 2 square root of 2 sine of square root of 2t, like all this. Yes, we can see. Good. Now, let's see. Another thing we can do is this and that can be combined. And when you combine this and that, it's just this and that is just a 2 over that. So the 2 will be gone, right? And then that's pretty much it. So I will just write this down. This is 1 over 4. I would multiply this in square root of 2, right? Again, this times this plus that is 2 over 2 square root of 2. 2 and 2 cancel, so we have the square root of 2 left on the bottom, and then 1 over 4 in the front like this. And then this part, which is sine of square root of 2t. Man, who wants to do the convolution, man? I don't know. Anyway, and then do this is minus 1 over 4t cosine square root of 2t, like this. And then we are done. Yeah? On the answer key, I rationalize the denominator, but I'm not going to do it right here because I did a lot already for you guys. So have a look, have a look, have a look. So just like that. All right, next, question number 19, right here. Originally, I'm debating to see which one I should show you. This one, just you factor and then do partial fraction. But I think in study, we did a lot of partial fractions already, so not so much. So actually, let me just get into how to solve differential equation with the Laplace transforms, yeah? Shall we? Let's go ahead and do that. And then I'll rearrange the I'll just do it in this order then. So question number 19. So it's this one. I have y prime and then plus 2y equals sine of 3t, and then we also have to have the initial condition y of 0 is equal to 0. And if you wonder why if we don't have an initial condition, we'll just go back to the person and say, hey, where's my initial condition, man? Anyway, this is how we're going to do it. First, you apply the Laplace transform to the equation. So go ahead, you can just do it like this. And this is the original. What you do is, this Laplace transform, you will take this equation in the t world to the s world, and then just mess around over there, right? Just do the algebra over there. And once you get it done, take the inverse Laplace and you'll get back to the t world. That's it. Let me show you. First thing first, the Laplace transform of y prime is the following. You get s times, and in this case, let me just make a note right here. if we take the Laplace transform of y of t, which is just the y function in the t world, once I'm in the s world, I'll write it as y of s. Right? I'll write it as capital Y of s. All right, here we go. So it's little s times capital Y of s, right? And then you minus the initial condition, which is y of 0. And in this case, it's 0, so I'll put on 0 right here. And again, this right here is just y of 0. It's s y of s minus y of 0. So this is what we have for the first one. Next, take the Laplace of 2y, you get plus 2 capital Y of s, like that. Next, we have this. You get this right here. It's the b value, which is 3. Oops, it shouldn't be in red. This is the 3, so I have the 3 right here over s squared plus 3 squared, which is 9, like that. All right, so that's pretty much the first step. Now, what you want to do is, you want to solve for what y of s is. That's why I said you have to do the algebra work in the s world, and then once you're done, take the inverse and you can go back to the t world. All right, so this is not so bad because you see only these two terms, yeah? So we have s plus 2 times y of s, which is equal to that, namely 3 over s squared plus 9, like this. And of course, we can just divide that on both sides. So we are looking at y of s is equal to 3 over s plus 2, and then s squared plus 9, like this. Now, we will take the inverse Laplace on both sides. And let me just write it like this. Inverse Laplace on everything. So, I'm sorry, the bracket is not the nicest thing. I cannot draw the brackets. The braces, actually. All right. The left-hand side will give us the little f of t. Sorry, y of t. I'm saying y. So the left-hand side is going to give us the little y of t. And now, we just have to work that out. And you see, this is why I didn't want to do the partial fractions, because we still have to do a lot right here. So, partial fractions in action. Let me just do it right here. So, we have, let me see right here, 3 over s plus 2, and then s squared plus 9. So I'll do one more for you guys, yeah? Let's see. First one is s plus 2, some number on the top. And then the next one, s squared plus 9, is bs plus c. Now, to figure out A, go back to the original, cover this up, and you ask yourself, how can you make s plus 2 equal to 0? S has to be negative 2. Put it here. Negative 2 squared is 4, plus 9 is 13. So A is 3 over 13. Now, for the B and the C, do the traditional way. Multiply everybody by the denominator. So I will end up with 3 by itself. Do this in your head, keep track, right? So you have 3 over 13. You want to have to multiply by this. S squared plus 9. And then plus bs plus c multiplied by s plus 2. Yeah, and then just work this out. This is 3 over 13 s squared, and that's plus 27 over 13. Yes, plus this and that is bs squared plus 2bs plus cs plus 2c. Good. Now, check this out. Here we have the, let's see. Here we have, oh man. Here we have this, yeah? 13. Let's just write it down. Here we have this 13, 3 over 13 s squared and all that. So I will say 3 over 13 plus b. And then, of course, this is the s squared term. And then plus this and that is the s term. So we have 2b plus c. That's the s term. Lastly, we have plus 27 over 13 plus 2c. Like this, that's the constant term. Which one is the easiest to do? Well, pretty easy, both. This right here has to be what? 0, because we do not have the s squared term on the left-hand side. So that means b is equal to negative 3/13. Good. Yes. And then, in that case, what's c though? Well, I don't know, I'll do it here because I have the coefficient here and I don't like that. So here, 2b, which is that negative 3/13, plus c has to be equal to 0 as well. So this is going to be positive 6 on the right hand side. So c is equal to positive 6/13, like that. So not so bad in my opinion. Yeah, not so bad in my opinion. Yeah, okay. All right, so let me just put things down together. First one, here we have to do the Laplace, inverse Laplace. A is 3/13. And then we have to do the inverse Laplace of 1/s plus 2. Yeah, let's just look bad. Now, b is negative 3/13, so we have to minus 3/13, and then inverse Laplace, and that's with s, so we have the s over s plus s squared plus 9, which is the same as 3 squared, right? And then, of course, make this longer. C is 6/13, so I will just put down plus 6/13, and then I'll just erase all this because we have all that already, right? 6/13, and then we have the inverse Laplace of C is 6/13. Yeah, well, lucky I put that down already before I erase. Anyway, 1/s squared plus 3 squared, like that. Whew. All right, now, ladies and gentlemen, first equation, right? First answer, right? The first differential equation with Laplace is equal to 3/13. This is e to the negative 2t, and then this is good. It's the cosine, so you don't have to divide whatsoever. Minus 3/13 cosine of 3t. This right here, you do have to do something. Here is 3. So go ahead and multiply by 3 and divide it by 3. And you can reduce, of course, so just reduce, so it's a 2. So 2/13 sine of 3t. And do we need to put down plus c? No, we don't. The beauty of doing this is that the constants were solved throughout the procedure already. So it's not so bad, right? So very good stuff. Right? So that was question number 19. All right. Question number 20. Next, we have the second derivative one. So y double prime minus 4y, and that's equal to 3t squared. And we have y of 0 is equal to 2, and y prime of 0 is equal to 1. Right, here we go. Go ahead and do the Laplace. This is just the original version. Now, first, this right here, we begin with s squared. So it's crazy already, okay? S squared, and then we get y of s. Right, Laplace of the second derivative is y squared. It's s squared times y of s, and then minus s of s times y of 0. So it's s times 2. So this right here is y of 0. Let me think. Is it y of 0 or y prime of 0 first? Man. It was y. All right. Just show you how we did that. Right? So Laplace transform of f prime. This right here is equal to s Laplace transform of f, and then minus f of 0. Yeah. Just like, yeah, like that. And then now I want to have the second derivative, so I will just put on f prime here, and then s, and this is f prime minus f prime. Oh yeah, I was right. Yeah, because this right here is just what we have right here. So you just put this down. So it's s double prime. Yes, I'm right over there. Yeah, and then minus f prime of s. Minus this, which is 1. This is right. So that's the second derivative. That's the first part. Then you continue. Minus 4 capital Y of s, and that's equal to, do the Laplace of here. Man, you have the 3 times n is 2, so you do 2 factorial over s. 2 plus 1. Man, why did I choose this big number? No, man. Anyway, let's go ahead and do this. Stop complaining. All right, this and that has to go to the other side. And this and that, we will just factor it. So we have s squared minus 4, and then capital Y of s. Okay? And then this and that go to the other side. So we have 1 plus 2s, and this and that, 3 times that is 6 over s to the third power, like this, right? And then we have to divide everybody by the s squared plus s squared minus 4. So y of s is equal to 1 over s squared minus 4. Serious? I have to do that many partial fractions? All right, I'll do partial fractions for one of them only. So this one, 1 minus 2s, or 1 plus 2s over s squared minus 4. Minus 4, and then plus 6 over s third power s squared minus 4, like this. God, why? Why did I do this to myself? All right, let's see. This partial fraction we're going to do in our head. Y of s is equal to the following. This right here, I need to have s minus 2, and then plus s plus 2. Now, check this out. To make, let me just write it down, s minus 2, s plus 2. To get this number, you have to cover up and let s equal to 2, yeah? Put it right here, so you have 4 plus 1 is 5 over 4. So it's 5 over 4. So let me just put this down right here, 5 over 4. And then here is s minus s plus 2, so you cover this up, you let s equal to negative 2. So you get negative 4 on the bottom. You put negative 4, so you get, so you put negative 2, so you get negative 4, and then 1 plus, so it's negative 3. Yeah, so it's like that. Oh man, seriously, I have to do a lot of partial fractions for this. Oh man. Why did I do that to myself? Why did I do this to myself? Why did I do this to myself? Can I skip this one? I don't know. Guess why not? Should I do it or should I not do it? All right. Okay, I'll do it. All right, so for this right here, let's see. So, man, this is going to be this 6 over s third power s minus. I really don't want to do this. So 6 over s third power s minus 2 s plus 2. Was there a way that we can? But still, it's going to be bizarre, regardless. Another way we can do it is just combine it as a big fraction first, and then just, okay, I'll do that. I will seriously do that. Man. All right, I have to really make sure I can finish this before they. All right, anyway, so this right here is divided by that, yeah? And you have that. So I will actually have to get the s to a third power right here. So let me just write this down. Divide this by s to a third power and multiply that. All right, so again, you will get the following. And I will divide everybody here. So what you will get is this and that, which is actually this and that is 2s to the fourth power, and then plus s to the third power, and then plus 6. Right? So just get the common denominator, all that stuff. And then I will just divide that right here as well. So we have the s to a third power here, and then divided by that, which is s minus 2, and then s plus 2. Okay. It's a horrible partial fraction. So 2s4 plus s third power, right? This is s third power. How can I make it s to the? Here we go. That's s to the third power. Plus 6. All right, and then this is s third power s minus 2 s plus 2. Now, the horrible thing with this is that you have to build all the powers. So first you actually have to something over s plus next one something else over s squared, and then plus next one c over s to the third power. And then you continue by doing this plus d over s minus 2 plus e over s plus 2. God. All right, good news. 3 of them we can use cover up. So let's do c first. Because for c, all we have to do is go back to the original and then cover this up. So I'll write this down. C is equal to when s is equal to 0. So you get on the top is actually 6 over, this is up, right? So you have negative 2 times 2, which is going to be, this is negative 3 over 2. Good. Now, when you have d, that's when s is equal to 2. So put the 2 into all that. Man, put the 2 right here. Don't put the 2 right here. This is 8 times 4. And then put the 2 right here. This is 16. That's 32 plus 8. And then that's 46. So that's 32. 46 over 32. And divided by 2. 23 over 16. 23 over 16. Does that look right? It should be 3 over 16. What the heck? This is just not cool if you... Oh my goodness. You know what? I wrote down the wrong answer. I wrote down the wrong question. So y of 0, okay. No, the y prime of 0 should be negative 4. This right here should have been negative 4. I'm so sorry. This right here should have been negative 4, so it matches with my answer key. So this right here should have been a negative 4, so it becomes plus 4. So if you put a 4 right to the other side, this would have been a negative 4. And this would have been a minus 4. I'm so sorry. And then this right here should have been a minus 4. S. All right, let's do it again. All right, C is equal to when S is equal to 0. That was so wrong. It was not 16, it's 6. Anyway, well, actually 6. Anyway, C is when S is 0. So you have 6 over negative 2 times 2. And that's negative 3 over 2. So that's good. And I think that works. Yes, that should work. All right, so that works, I hope. Yes. Now, D is when S is equal to 2. You put the 2 into here, and here. So let's see. 2 in here, this is 16. That's 32, yeah? And then 2 in here is 8. That's 32, so it's 0. So you have 6 on the top. Over, you put 2 here is 8. You put 2 in here, it's going to be 4. So you divide by 2. So it's 3 over 2, 16. Good. All right. Lastly, E is equal to when S is equal to negative 2. When E is equal to negative 2, yeah? And you put it on the top. This is 16 times that is 32. And then negative 8, 32, so it's 64. And then plus that is 70 over, you put a negative 2 in, here is negative 8, times, you put that is negative 4. Am I right? Yeah. And then divided by 2. Man, it's 32 over, no, 35 over 2 is 16. 35 over 16. Okay, so far so good. It's matching my answer key now. So far so good. Let's see. What's A and B then? God, I really don't want to do this. All right, let's just do it. A, you can do it like this, right? You see how we have used S, all these numbers, yeah? These numbers are the S numbers that we use. So what you can do is you can just let S equal to whatever else that you want. So this S is equal to 1. And now let's do this in your head. Put 1 in here. This is 2. And that's minus 2. And then we have, that is 4. Yes? Good. 1, negative 1, and 3. So just like that. So that's one S. So A is, I don't know actually. A over that plus B over 1 squared, just that, so it doesn't matter. And then C is that, so it becomes minus 3 over 2. And then D becomes, D is this, yeah? But S is 1, so it becomes minus. So remember, 1 minus 2 is negative 1, and D is that, so it's minus 3 over 16. 1 in here is 3. 3 put it here, so it becomes plus E, which is that, 35 over 16, but you have 3 like this. Man, I'm not making the, this is negative 4 over 3 equals plus B. This is just not fun to do. Man. Multiply by 8, negative 24. Negative 24, so negative 27 over 16. But I have to multiply by 3. So it's negative 81 over that. So negative 81 plus 35. Negative 81 plus 35. Man. 46. No. Yes. Negative 46. 46. So it's negative 46 over negative 46 over 3 times 16. God, this is just not fun to do. Okay, I will let you guys figure out the rest, okay? I think, according to the answer key that I have left, right here, I need to save some time because I need to finish the other questions. So, let's see. This is done. That's done. And this is also done. And now they are right for sure. So this right here is giving you a constant. So this A should have been negative 3 over 8. It should be negative 3 over 8. And then the B, it should be 0. Because there's only 4 terms on the answer. So it should be 0. So if you check, you will see. Isn't that right though? If this B is 0, let's see. Negative 4. I don't think so. Something is wrong. I don't know, man. But just go ahead and do it on your own. All right. Okay. So the struggle is super real. Anyway, A is negative 3 over 8, S. So negative 3 over 8. And then you have the S right here, so over S. And then B is 0, C is that. So C is this, so it's minus 3 over 2, and then you have the 1 over S to the third power. 1 over S to the third power. And then D is 3 over 16. So you just put a 3 over 16, and then you have the 1 over S minus 2. Man, a lot of work. S minus 2, and lastly, you have the E, which is 35 over 16, plus 35 over 16, and you have the 1 over S plus 2. All right, ladies and gentlemen, I'm so sorry about this, but here we go. Take the inverse Laplace on everybody now. Right? So just calm down a little bit. I know I'm the only one who's nervous. Right? So the first one you get is negative 3 over 8. Next one, notice that the n is equal to 2. So you actually get to, you have to multiply by 2 factorial and divide it by 2 factorial. So you actually get negative 3 over 4, and then t squared, and then plus 3 over 16. A is 2, so it's 2t, and then plus 35 over 16, e to the negative 2t, like this. Yes. All right? So, just like that. Yeah. Hopefully, your teacher let you use another method to solve this, because this is actually not the best method to solve this particular differential equation. It might be easier if you use the indeterminate coefficient. I think I'll do that for the next differential equation marathon. So the higher order differential equation marathon, right? All right. So 21. Y double prime minus 2y prime minus 15y equals 0. Y of 0 equals negative 2. Y prime of 0 equals 1. So these are what we have. Now, go ahead and get to work. Laplace in action. Now, this right here is S, Y of S minus, we have, S squared and that, and is S times Y of 0 first, which is negative 2. So put on negative 2. Again, this is Y of 0. And again, S should be in red. And then minus this, which is 1. So again, this is Y prime of 0. So that's the first part. Next, we have the minus 2. So we have to do minus 2. Laplace transform Y prime is S. And then Y of S. And then minus, right? But it was a minus 2, so I have to do minus, and then the 2, and then we have to multiply by what? multiplied by y of 0, which is negative 2. So again, this is the y of 0, right? And then minus 15y of s, like so, equal to 0. All right, not so bad. Hopefully not. All right, we have this, and that. The other ones have the y of s, so we can factor that out. We have s squared minus 2s, and then minus 15. And if you notice, this right here is actually from the original. Very cool, huh? And then you have the y of s. And I'll put the other things to the other side. So this is negative 1. This is minus 3, so which is minus 5. Sorry, minus 1, minus 4, which is minus 5. Put it to the other side, so it becomes 5. And so we have negative 2s plus 5. Now see, this is why I had to write the s and 5. Anyway, I'll stop. All right, so this is y of s equals negative 2s plus 5 over that, factored out already, which is s minus 5s plus 3, like this, all right? So, of course, I can just do the partial fraction right here for you guys. This is nice and easy. S minus 5 plus some other number, and this is s plus 3. To figure out this number, go back to this, cover this up. S has to be 5. Put it here, negative 10 plus 5 is negative 5. I promise I didn't do this on purpose. I didn't know there were so many 5s, right? I'm sorry. So it's negative 5. Okay? Negative 5. And then put a 5 in here, so it's negative 5 over 8. Now, for this number, go back here, s has to be negative 3. Put it here is negative 6, so it's positive 6 times plus that is 11 over negative 3, right? Over there is negative 8, like this, yeah? So that's pretty much it. Now, I will tell you, let's go ahead and do the inverse Laplace. So I will get y of t is equal to, here we have negative 5 over 8, that is right, negative 5 over 8. And this is e to the 5t, and then minus 11 over 8, e to the negative 3t. Much better, huh? Yeah, much better than the earlier one. So that's it. And this is also a way to show why when you have this kind of things, you end up e to the whatever. But yeah. Okay, number what? That was 21, now it's 22, yes. Number 22, we have y double prime plus 16y, and that's equal to cosine of 4t. And we have y of 0 is equal to 0. And we have y prime of 0 is equal to 1. All right, so now go ahead and do the Laplace. Here we go. For the first one, we have s squared. For the first one, we have s squared y of s minus s times this, which is going to be 0. That's nice. Minus that, which is minus 1. Okay, that's the second derivative, right? The Laplace of second derivative, and minus 16 plus 16, and then we have that is just y of s. And that's going to be, we have s on the top, and then this is s squared plus 4 squared. So that's pretty much it. It's not the Laplace that's bothering you, it's the partial fraction that's going to bother you, right? Anyway, that's out. This is one will be on to the other side. So here I'll factor out s squared plus 16, and then we have y of s. So that's good. 1, bring that to the other side. So So we have 1 plus s over s squared plus 16, like this. Okay, divide everybody by that. So we get y of s equals 1 over s squared plus 16 plus s over s squared plus 16 square, like this. This right here is not so bad, so I will just go ahead and write this down for you guys already. Perhaps I'll give you guys some Christmas color. Why not? If the Laplace is in red, then the inverse Laplace should have been green. But anyway, at this one time. Y of t, this right here is going to be what? Well, I need to have a 4, so multiply by 4 divided by the 4. So, because this is 4 squared, so we get 1 over 4 sine of 4t. Very good stuff, yeah? Now, for this one though, well, you have to do the things that we did. The derivative of this will actually give you guys something like that, so check this out. So, if you have the Laplace inverse, if you differentiate this with respect to s of that, which is s squared plus 16 to the negative 1, right? Well, if you would like, you can put a negative right here. In that case, you just do t of f of t. T of f of t, right? Which is, this is supposed to be f of s, and then this is supposed to be little f of little t. Yeah, but if you know this already, which is sine we got that, so I will put this down right here. So it's 1 over 4 sine of 4t. I believe we have the 1 over 4. That is correct. I hope, yes. Yeah, it's correct. All right, so if you do the derivative, this right here all the way in front, minus 1, and then do the chain rule. So if you look at the inverse Laplace, the derivative of that is going to be s squared plus 16, and then you square that, and then if you look at the chain rule, you have the 2s. It's equal to this, which is t over 4 sine of 4t. Man, doesn't this look really pretty? Really pretty. Yes, it does. Divide both sides by 2, so you get this right here is plus. Oops. This right here is plus, and I put down as 1 over 8. Let's divide the 2 right here, so we get 1 over 8, then t sine of 4t. Huh? Not so bad if you know how to do the inverse Laplace and do it a quick way sometimes. Yeah, just like that. Right? All right. 2 more to go. Number 24. No, number 23. Sorry, because I changed the question. Here we have y double prime plus y equals the unit step function. And we have the t minus 3. And we have y of 0 is equal to 0. And then y prime of 0 is equal to 1. Now, here is the deal. Original Laplace, of course. Now, let's go ahead and get to work. Right here, we can just nicely write down our thing, which is s squared y of s minus s times y of 0, which is 0, and then minus y prime of 0, which is 1. Right? And then you continue, you add y of s, because this is just y, so it's y of s in the s world. And now you have to remember what's the unit step function in the s world. Well, it's going to be something over s, and that's e to the negative a s, so it's negative 3s, like that, right? So that's pretty much it. And now go ahead and just do the work. This is out, so you have the 1, so put it out to the other side. So we have the s squared plus 1, and then we have the y of s. That's equal to 1 plus this guy, which is e to the negative 3s over s. Divide everybody by that guy, so we get y of s is equal to 1 over s squared plus 1, and we add e to the negative 3s over s times s squared plus 1, like this, right? All right, so here, now we can just do the inverse Laplace. Oops, wrong color, but whatever. Here, I'll just do this right here first. Y of t. This right here is equal to what? Sine, yeah? Really good. Sine t. Well, for this one, it's not so easy. We have to do the partial fractions again. Why did I do that so many with partial fractions, man? For this one, I will take some time to do it. What you do is ignore the e to the negative 3s for now, right? So just focus on this part. So I will just write this down for you guys. I'll put this down. So note 1 over s. Let me just write down everything in blue. No more. I'll still keep it. I will still keep my challenge. 1 over s times s squared plus 1. This is equal to 1 over s plus, no. It's not 1 over s. It's 1 over s, but I'll show you. Anyway, a, b, s plus c. To figure out a, you put this to be 0, so a is equal to 1, so that's good. Now, let's see what we get. This right here. Multiply everybody by the denominator. So multiply everybody by s squared plus 1. Let's just do like this. Multiply, we get 1. Multiply, this is just s squared plus 1. Multiply, we just get plus. Distribute the s, yeah? So we get b s squared plus cs. Just algebra. And as we can see, this is b plus 1 s squared. This is plus cs and then plus 1. One match already, so you can see b plus 1 has to be 0, b is equal to negative 1, and c has to be 0. So that's the idea. Now, for this one, this is how you have to do it. For this, yeah, you actually have to do this first. Let's do the inverse Laplace of the part without the e to the negative 3s first. We have 1 over s, and then b is negative 1, so it becomes minus s over s squared plus 1. So this is the part without the e to the negative 3s first. And if you do that, this right here is just 1, and this right here is just cosine t. So this right here is it. And I will call this to be our f of little t, right? Why? Because whenever you have e to the negative 3s, the s right here, you will get the unit step function as well. And you will be unit step function of t minus 3, like that. So we will have this as the factor. Well, when we go back, what you have to do is this portion has to be f of t minus 3. So be sure you put the t minus 3 into this t. So we get 1 minus cosine t minus 3. Like that, right? So that's the answer. It wasn't the worst one. The worst one was the one that we struggled with because of the partial fractions. But this right here is it. Right? This right here is it. Have a look. Okay, ladies and gentlemen, here is the last one. Okay, my hands are always so dirty. all the markers, man, it's like not the greatest marker that I'm using. Okay, y double prime minus 4y prime, and then plus 5y. This right here gives you 0, and y of 0 is equal to 1, y prime of 0 is equal to 2. I really want to do this one because if you do it with the usual way, meaning if you let y as e to the rt and then you get a characteristic equation, you get complex root for that. With Laplace, it will explain why you end up with the answer like that as well. So let's do it. First, original Laplace. No big deal. Here we go. Y double prime, we get s square y of s minus, next is s times y of 0, which is 1, and then minus 2. Right? So this is the second derivative portion. Now we have the negative 4, so we have negative 4 right here. And then for the y prime, we get s y of s. And then it's going to be a minus, but I will have to distribute the negative 4. So it becomes plus 4 times f of times y of 0. So times 1, like that. Lastly, 5, and then this is y of s. And then the best thing is that the inverse Laplace of the original Laplace of 0 equals 0. Huh? So have a look. Now let's just do this. All right. So here you see that this part, and that part, they all have the y of s. And the other ones, they are just numbers actually, which is, no, they are not just numbers. Anyway, s squared minus 4s plus 5, and then you have the y of s, right? After we factor all that. Now this is minus 2, this is 4, so it's 2. Bring that to the other side, becomes negative 2. Negative s, here it's actually positive s, and then minus 2, yeah? So do that in your head. And finally, you can just go ahead and divide that. So we have y of s equals s minus 2 over that denominator. Guess what? We have to complete the square. So let's do this right now. Complete the square, actually, that complete the square, we get s minus 2. Very good, huh? We get s minus 2 square plus 1. This is so good, isn't it? Again, complete the square in your head, right? Huh, what's the answer for this one? We did a few of this already. Let me just write this down for you guys. Finally, I will give you guys the green for the inverse Laplace. This and that match like very nicely, huh? So let me just tell you y of t. This is the one with s, so you get the cosine version. So you have the cosine, and this is 1 square, so this is just 1, yeah? So just cosine t. And you just have to multiply by e to the a is 2, so it's e to the 2t times cosine t, and we are done. Whew. This is the answer at the end. That's it. All right, so, wow. All right, so the only question that I was not able to finish completely was question number 21 because I slightly make it slightly too hard. Yeah. But anyway, hopefully you guys will find all this to be helpful. Again, 24 inverse Laplace transforms for you guys. This is the inverse Laplace marathon, and let me know what you guys would like to see next, right? And of course, let me show you guys my medal. This is a smaller one, but this is the one from 2005. This is actually my first one that I actually trained for it. My 2004, it took me 6 hours, 30 minutes because I didn't really train for it, but this one I did. And the time was like 6 hours. I mean, the time for this one was 4 hours and 30 minutes something. Yeah. So, oops, I put it down. I don't want to use my right hand because my right hand is so dirty. All right, feels good. So this. Okay, hopefully you guys find all this to be helpful. Again, all the links will be in the description for your convenience. And if you have any questions, just let me know. And I did spend a lot of time to prepare all this and then work that out. So if you enjoyed my video, please give me a like. Thank you guys so much. And as always, that's it. Bye.